Okay, well, thanks very much. So I first started my relationship with SUSY in 1979. And then for many years, we were kind of in a monogamous relationship. I'm not sure whether our relationship is still monogamous. I'm not sure whether that's my fault or Susy's fault. But anyway, I still love SUSY. And I'll describe to you why. And I'll talk about the prospects for looking for supersymmetry, not only in the light of LHC results, but also the measurement of the muon anomalous magnetic moment. And I'll discuss some of the specific channels that seem to me to offer interesting prospects for discovery in runs greater than or equal to 3 at the LHC, including, of course, high luminosity. And I may say a few words also about the prospects for proton decay. So, supersymmetry is still my favorite scenario for what lies beyond the standard model. And I would say that the first couple of runs of the LHC have actually provided us with additional reasons for liking supersymmetry. So as I think you know, there's an issue with the stability of the electroweak vacuum in the standard model. Supersymmetry fixes that. As we heard in the previous talk, supersymmetry made a successful prediction for the Higgs mass. It also predicted correctly that the Higgs coupling should be within a few % of their standard model values. And those are all new things in addition to all the traditional motivations from naturalness, grand unification, string theory, inflation, and dark matter, and so on. So I'm going to be saying quite a bit later on about G-2, but I'm going to proceed in a chronological order, more or less. And I actually got interested in supersymmetry in G-2 back in 1982. So SUSY and I had already been going out together for a few years. Anyway, we did a calculation of the one loop contribution of supersymmetry to the anomalous magnetic moment of the muon. That was, of course, very early days before the idea of supersymmetric dark matter, for example. And it was also before the Brookhaven experiment. So the Brookhaven experiment was started in 1984 and completed in the early 2000s. So as you know, the final result of the Brookhaven experiment indicated a tantalizing disagreement with standard model calculations. So these are the values of G-mu-2 measured with positive and negative muons, the average. And these two theory estimates here are data-driven estimates based on E plus E minus goes to hadrons data and tau decay data. So 20 years after my first foray into supersymmetry in G-2, I had another bite of the cherry, this time also taking into account the dark matter constraint. And this picture here shows you what we had then as the preferred range of supersymmetric model parameters, including G-2 and including the dark matter constraint. Obviously, things have got a lot more refined in the intervening 20 years, and I'll come back to that later on. But the importance of G-2, of course, is that it suggests that at least some supersymmetric particles, notably at least one smuon and the neutralino, should weigh no more than a few hundred GeV. Okay, so that was all before the LHC got started. And as Philip has eloquently described, the LHC, while discovering the Higgs boson in agreement with supersymmetry, also so far not discovered supersymmetry itself. So there's a whole industry of modeling LHC constraints on supersymmetric model parameter spaces. And we had a very nice talk about this just before the break. So this is something that I've been involved with over the years in the master code collaboration. And these are some results that we haven't released yet, simulating neutrino decays using a fast simulation called FastLim. And I think one of the things that I would emphasize that if one wants to do a global analysis of LHC constraints, one has to, as has also been mentioned previously, take all possible decay modes into account because they can dilute the signals that you would expect in simplified models. And rather than sort of combine using cuts, it's best to try to model and combine the likelihoods for all the available channels. So this is something that we've been doing in the master code, as I said. And so one class of models that we've been looking at is gut-based models, where you have some universality assumption at a high scale, you calculate the normalization, and in this type of scenario, you get relationships between the squark and slepton masses and the gluino and the neutralino mass. And if you do that, you find a very small contribution to G-2. Absolutely no way that you could make a significant modification of the standard model calculation. And this is basically because the smuon is pushed by the available constraints on strongly interacting particles up to very high masses. Now, this is not the case if you adopt a more phenomenological approach and basically allow the soft supersymmetry breaking parameters to float. And the sort of name for this framework is the Phenomenological MSM or PMSSM. And this again taken from a paper that we did a few years ago, shows you the constraints that you get on the neutralino mass, the smuon mass, and it demonstrates that in such a scenario, you can accommodate the G-2 result. So I draw your attention here and in subsequent plots to these blue curves here, which are the global likelihood function with, in this case, not a complete set of LHC13 results, but a representative set, and including the G-2 constraint. So PMSSM can accommodate G-2 and LHC. Now, that said, although such a scenario basically requires, for example, some sleptons and neutralinos to be relatively light, the squarks and the gluinos could be very heavy. They could be beyond the reach of run 3, beyond the reach of high luminosity LHC, and well into FCC range. But there are still interesting possibilities for the LHC. So digging down a little bit, here I show you a bit more detail from this analysis that we did a while back. Again, we did analyses with and without the G-2 constraint. And the one on the left is actually with the G-2 constraint. This color coding here corresponds to the various different mechanisms for bringing the dark matter density into agreement with astrophysics and cosmology. So different color coding for different mechanisms, in particular different co-annihilation mechanisms that have been discussed in previous talks. I draw your attention here to slepton co-annihilation. So this is co-annihilation of the neutralino with a selectron and or a smuon. And this will play an important role in what I'm going to say in a moment. Okay, so what are the constraints on the squarks and the gluino masses in such a scenario? Well, if you include G-2, you get results which are really quite similar to the constraints put about by the LHC collaborations. I'm not going to go into them in any more detail. So how about stops? So here again, on the left, I've got an analysis with G-2, on the right, an analysis without G-2. And you see it in both cases, although the stop could be quite heavy. There's also a little island here, which is allowed at least at the 95% confidence level with a relatively light stop. And just for good measure, I note that in this region, slepton co-annihilation dominates. So again, from our previous paper, on the left, we have an analysis with G-2. We have the global likelihood function for the stop on the left, showing that there is a window for a relatively light stop around 500 GeV or so. It's not the case for the bottoms. They probably weigh more than a TeV or so. So that analysis did not include the current LHC 13 constraints. So here is one from ATLAS, the one from CMS that you've seen previously. It is very similar, but I note that here also you get a window allowed for a stop that weighs about 600 GeV, very close to this window that we found here. So this means that I think going forward, it would be very interesting, LHC round 3 and of course High Luminosity LHC, to push on this low mass stop window, which occurs when you've got a small mass difference between the neutralino and the stop. This is still a very interesting possibility for all sorts of naturalness reasons. Now there's been some discussion of the possibility of a long-lived next to lightest supersymmetric particle. So again, the blue curve here is including G-2 in the constraint set. Green is excluding. It's easier, we found, to get a long-lived supersymmetric particle if you drop G-2, but it's still possible with G-2, as is shown again here by the blue curve. Okay, so now let's focus down on the smuon and the neutralino. So again, on the left here, we have an analysis, likelihood analysis, including G-2. On the right-hand side, we drop G-2. And you can see here a preference for light smuons, light neutralinos weighing a few hundred GeV, right up to the equal mass limit. And you see again here the potential importance of lepton co-annihilation. Okay, so all that was before the Fermilab G-2 result. So here's a Fermilab G-2 experiment, which to the untrained eye looks the same as the Brookhaven experiment. That's because the magnet is the same, but maybe got a new paint job, but of course it also got a whole bunch of additional new electronics. So as you know, the Fermilab result announced earlier this year agrees really remarkably well with the Brookhaven result. The dominant contribution to the uncertainty here is actually statistical. The systematic error is relatively small. You can combine the two results. This is the experimental average. This to be compared with the standard data-driven calculation within the standard model. And you get a deviation of 4.2 standard deviations. Now, this theory calculation that I showed you, as I said, it's data-driven, and it basically comes from this theoretical white paper, which discusses all sorts of theoretical aspects of the calculation, but focusing particularly on the calculation of the leading order vacuum polarization. So this makes up for something like 3/4 of the the low mass region below 1 TeV, 1 GeV makes up for about 3/4 of the total hadronic vacuum polarization contribution to G-2, 3/4 of the total contribution, and about a half of the uncertainty. So obviously it would be desirable in the future to improve these low energy measurements, in particular because there's some residual discrepancy between the Chloe and Barbara experiments. Okay, so this theory data-driven estimate is shown here. This is the black point with uncertainties written here. And that came out before the Fermilab result. So here you see the Brookhaven result and the eventual Fermilab uncertainty goal, but it will take a while for Fermilab to reach that uncertainty goal. Now, in addition to these data-driven estimates, you also see ab initio lattice calculations of the hadronic contribution to G-2. And you also see a hybrid approach, which I'll describe in just a moment. Now, there's been a lot of excitement generated by one particular lattice calculation put out by the BMW collaboration also earlier this year, and I'll come back to that in a moment. Now, when you're doing a lattice calculation, you have two problems. The first problem is that a lattice has a hole in it because the lattice spacing has a certain size. And also the lattice as a whole has a certain size. So you have a problem at short distances in the holes, and you have a problem at large distances because you don't have extremely large lattices. So there's a sort of intermediate window where the lattice calculation should be very good. And it's actually a region where you can compare directly with the experimental data. So what the UK QCD lattice people did was they combined their lattice calculation at intermediate distances with data at very low energies corresponding to very large distances out here, and a perturbative QCD estimate of the high energy contribution corresponding to the very short distances. And as you can see in this plot here, they basically got a result which is very similar to the standard data-driven calculation. But BMW got something different. So I'm not an expert on lattice calculations, and I've talked to a lot of lattice people. I've heard presentations by lattice people. I'm not sure that they fully buy into the BMW calculation, or that they necessarily say it's wrong. I just present to you the BMW result and just make a couple of comments. So one is that because of the finite size of the lattice, there is a significant uncertainty attached to the extrapolation to the continuum limit. And this is actually the naked lattice calculations, but then they have to improve it with some model calculation, which brings it up to here. So it's actually quite a substantial correction here, which is comparable with the spread in the various different theoretical calculations. And this, I think, needs to be scrutinized by the community. There's also an issue as to whether the BMW calculation is compatible with the data. So I think everybody agrees that there is a mismatch. And the question is whether the mismatch occurs at low energies or whether it's at high energies. Now, if it's at high energies, then you have a problem with the precision electroweak measurements at the Z peak. If it's at low energies, well, then you have a problem with the data. And that's illustrated here. So here you've got various attempts to predict what the low energy data should be if you take literally the BMW calculation, and you see the agreement is not so great. So I don't know what the conclusion of this is. I think this is an ongoing discussion. Okay. So, of course, immediately after the Fermilab result came out, there was a tsunami of theoretical papers. And I tried to keep track of them for the first month or so, and then I just gave up. Anyway, here's the first month or so of papers, and I've color-coded them according to which supersymmetric framework, which framework they adopted. And you see a lot of them adopted supersymmetry. That's what I'm going to focus on now. Okay, so let's look again at the one-loop calculation in supersymmetry. So you've got diagrams involving muons and neutralinos, and diagrams involving neutrinos and charginess. Now, the ones of interest for me are actually these ones here on the left, the muon and the neutralino. And if you're going to calculate those, you have to take into account the fact that there's two different types of muon, partnering with the left and right-handed muons. And of course, there's 4 different neutralinos. So anyway, these are the the relevant results from calculating the diagrams, I would emphasize that an important role is played by a diagram which mixes left-handed and right-handed muons. Okay, so now let's just refresh ourselves as to the LHC limits on relatively light leptons. So this is a compendium plot taken from ATLAS, where they show the current constraints. So this big yellow one here is a sort of generic missing energy constraint. And then in orange here, we have a dedicated search for a compressed spectrum with very similar masses for the muon and the neutralino. And then what we also have here is various different values of tan beta, mu, and M2, which reproduce the value of G-2. Now, a caveat that I would make is that this orange region, as far as I can make out, is the envelope of the constraints on both left and right-handed muons. And the constraints on right-handed muons are actually significantly weaker than the constraints on left-handed muons. And this is illustrated explicitly in this pair of plots. I think it's from the same ATLAS paper. So this again is the generic missing energy search. This is a sort of channel where the spectrum is compressed. And this is a dedicated analysis looking for small mass difference. What you see here is that the constraint on the right-handed muon is quite a bit weaker than the constraint on the left-handed muon. And this is just because the production cross-section is different. So looking forward, I hope that the LHC collaborations are going to fill in that channel that we were looking at, but they're going to pay careful attention to this feature of this muon spectrum. Okay, so there have been various papers analyzing the prospects for discovering supersymmetry in the light of G-2 as well as the LHC. Here's a couple of plots from a paper by Chakraborty and collaborators, where they take into account not only G-2, but also the relic density, also dark matter scattering, and the LHC constraints. And so these red points here are the ones that they find are favored. I should say that this analysis is in a sort of PMSSM-like analysis. Now, one thing which I've been doing recently is I've been trying to bridge the gap between this very phenomenological supersymmetry analysis and the sort of gut-based analysis. So in guts, you've got a lot of universality relations relating, for example, squark and lepton masses. Now, we've been looking at a model called flipped SU5, which is a gut, but with an additional U1. And the point about this additional U1 is that then the right-handed lepton, so for example, the right-handed muon, is in a different representation from the squarks and the left-handed leptons. And you've also got an additional, U1 gaugino mass, which is in principle different from the gaugino mass appearing, for example, for the gluino. So the gluino and the neutralino are decoupled, and the right-handed muon is decoupled from the other squarks and leptons. So this is a picture taken from a first paper that we wrote earlier on this year. So here in blue and in red, you have the relevant LHC constraints. So here, we're going to be interested in a light right-handed muon. And for that, as I commented, constraints are relatively weak. We've also shown here the LEP constraint and also the constraint from requiring that the lightest supersymmetric particle be neutral, not charged. And these points are color-coded according to the contribution that they make to G-2. And you see the points that make a big contribution to G-2 are concentrated in this channel here, where you've got a compressed spectrum going up to several hundred GeV. The best fit point is actually right at the limit of LEP. And here I show a table with the input parameters and the predictions for various different particle masses and other quantities. So in this type of scenario, there would definitely be opportunities to see a light, muon, and neutralino at the LHC. So I wish the LHC collaborations good luck with closing that neutralino muon channel. On the other hand, most of the other particles may be too heavy to be discovered. So for example, the left-handed muon, 1600 GeV, squarks several TeV. Now there's considerable uncertainty in this, but I think it's illustrative that in this particular scenario, you should really focus on the muon and the neutralino. And it's interesting that in this scenario, you basically for free get the right dark matter density, and that's enforced essentially by co-annihilation of the neutralino with the right-handed leptons. So in this model, you can get a much bigger contribution to G-2 than you can with a CMS and SEM. Maybe not quite enough to fully reconcile the data-driven estimate with the data, but certainly enough to cover BMW. So my opinion on this is that flipped SU5 does enough to basically stop us worrying about the experimental result for G-2. What you have to do, Philip et al., is to find that bloody muon. So I promised a short remark about proton decay. We also had a quick look to see whether we could also get proton decay at a rate detectable with the hypercameo-candy detector. So here you can see that there's a strip in parameter space where we get a big contribution to G-2. That's also a range where we get the right dark matter density. It also contains a small region where proton decay is accessible to hypercameo-candy. It also gives you the right Higgs mass. It does everything, including make a good cup of coffee. And this is what we call the quadrifecta region, where we do pretty much everything that one would like to do. And again, this is a table showing what the particle spectrum looks like. Again, muon and neutralino are light. Other supersymmetric particles are heavy, good dark matter density, good Higgs mass, and detectable proton decay. So to conclude, a lot of people are down on supersymmetry at this moment, but my motto is nil carborundum. Don't let the anti-supersymmetric bastards grind you down. For me, it's still the best motivated BSM scenario. G-2 may indicate that finally we're seeing some physics beyond the standard model. It could be supersymmetry, which could also provide the cold dark matter and observable proton decay, and would give you interesting possible LHC signals. So I focused in the latter part of my talk on light leptons. In the earlier part of the talk, I emphasized light stops. And in between, I also had a little remark about long-lived next to lightest supersymmetric particle. So I think everybody knows this picture. Nobody knows what they were discussing. I can tell you. The people on the left believe in supersymmetry, not the guy on the right. So I think there's a clear message there. One can also consider this picture here, where the visible matter in the universe is the tip of some iceberg, which contains a lot of other physics, dark matter, G-2, and maybe with run 3 and beyond, the standard model will finally be sunk. Thank you.
Thank you very much, John, for this very interesting and comprehensive talk. I already see a hand up by Javi. So Javi, please ask your question.
Oh, thanks, John, for a very nice talk. You showed that the PMSSM11 could allow for the G-2 discrepancy. Is it the going to 11 parameters that helps you more, or throwing away the RGEs? And could you achieve the same result by just going to 11 parameters and keeping the RGEs?
This sounds very similar to the question that you asked me last time.
Oh, okay.
That's right.
So we haven't done a systematic analysis of that. I think that the flipped SU5 example that I showed you later on is a sort of a step towards answering your question. Because there you have more parameters than the CMS. And you also have the RGEs. And there we found that, for example, it is possible, as I mentioned, to have a relatively light smuon and a much heavier squarks and leptons. So it is possible within that, I think it's 7 parameter framework. So I'm sure that if you went to 8, 9, or 10, you could also do it.
Thank you.
So, by the way, are you still in your hut in northern Wisconsin?
No, I'm in Madison now.
Okay. Back to COVID.
So the next one up is Pietro.
Hello,
Pietro?
John. Hi. So I was just curious about a statement, one of the motivational statements that you made in the first slide about, okay, apart from the supersymmetry predicting relatively light Higgs mass, you also mentioned that it predicts that the couplings are standard model-like. I wanted to know what is the reasoning behind, because it happened to me this summer to have to quarrel with anti-SUSY theorists who was telling the experimentalists that the fact that you appear to be in the decoupling limit of the MSSM, if you are in the MSSM, means that there is fine-tuning, and so you are somehow reduced to the corners of the parameter space. So what was your idea when you said that it's a prediction that the Higgs should be standard model-like?
So what I meant was that if you do a global fit, either in the CMSSM or the PMSSM 11, which of course is less restrictive, and you look at the Higgs couplings, you find that the Higgs couplings tend to be close to what they are in the standard model. So I'm afraid that I think in the stack of slides that I have for this talk, I don't have some plots that show you that explicitly. But if you look in some of the papers that we wrote a couple of years ago, you'll see that feature, that we actually displayed what the global fit predicted for the Higgs couplings, and they were similar to what they are in the standard model.
Okay.
But there was scope for deviation. It could be 10% or so, but it wasn't going to deviate by a factor of 2. And I might mention that these anti-SUSY people often tend to be people with composite models with strong interactions, which a priori are going to give you bigger deviations from, or liable, or possibly may give you larger deviations from the standard model.
Yes, I will not name them, but it was one of those people.
Okay. I don't see any other hands, so maybe I take my privilege of the chair and ask you one question, John. So again, thanks for this very clear and very nice, very hopeful discussion of SUSY. As you know, I'm also one of the big believers. What I wanted to ask you was, in the case of your flipped SU5 or versus PMSSM11, is there any difference in the preferred masses of the charginos and the neutralinos, the heavier ones? Because I noticed only for the lightest, the best fit point was similar, but I want to know more whether.
So I'm not sure that I caught the question. So,
but the question really is that between your G-2 in flipped SU5 and in PMS-SM11, whether the anatomy of the heavier chargino neutralinos is any different or is it the same of your loved region where the the heavier ones, the lighter one.
I don't think you're going to find a close relationship between them, but let's just look at it. So here we've got a heavier neutralino and chargino weighing a little bit over 2 TeV. Okay, and then the heaviest neutralinos weigh more like 5 TeV. Okay, so now let's go back up here.
Yeah, okay. No, then I think I have kind of the answer to my question.
Yeah, so here in this particular PMS-SM11 analysis, the second neutralino was actually quite light, quite similar.
Yeah, so actually, I guess going forward, what I really wanted to say was that apart from this, because of G-2, one wants to think of light muon and light neutralino with small mass differences. But in general, a lightish electroweak sector is something that is still very much okay. And that is electroweak phenomenology at HL-LHC should be a point of focus there, is what I wanted to ask your opinion on.
Absolutely, absolutely. So for example, here you have a lighter chargino and a second lightest neutralino, which are relatively light. Now that doesn't happen in flipped SU5 because those particle masses are constrained by the
because they are tied to the
unification conditions that you apply.
Exactly. That is what I wanted to kind of bring out, that this might be something that is could be a point of focus for the electroweak phenomenology at LHC.
Right.
Okay. So are there any, I don't see any more questions. So let us thank both the speakers of this Future Outlook sessions for having provided us with a wonderful and very hopeful future that and also pointing out that firstly, SUSY is still very much alive. Let us not let the detractors of the SUSY not discourage us. But more importantly, what Philip also said equally importantly, that let's think of discoveries and not just exclusions. So with these two, I once again thank both the speakers for the excellent talks